Hello, and today we're going through uncertainties and their errors for A-level physics. So let's get started. So first, let's introduce what uncertainties are. So when you measure something, there's always uncertainties in your values. And this is caused by experimental errors. For example, when you have a ruler like this and a block like this, and when you take different measurements from either here, here, or here, you could get different measurements of where the block is just because of the way you look at it. So for example, when you take a measurement from here, it's going to look like it's this length. However, when you take a measurement from here, it would be the correct length. And if you take a measurement from here, it would look like a different length as well. And this is called parallax error, caused by observing different measurements from different angles, and you'll get different values. Now let's move on to finding uncertainties. Say we wanted to measure the volume of a block like this. When we take measurements of the length, the width, and the height, we can take multiple measurements of each one, so we can find an uncertainty value for each measurement. So if we make a table of readings, and we have our first reading, our second reading, and our third reading, we can take a mean and find a range of the readings, and we can use this to find our absolute uncertainty of each value of the length, width, and height. So this is our length in centimeters, this is our width in centimeters again, and this is our height in centimeters again. And remember to always leave your units in the table titles, so you don't have to keep writing the units in each box. So say we have readings of 7.6, 7.5, and 7.6 for the length, and we have readings 5.0, 5.1, 4.9 for the width, and 1.6, 1.7, and 1.7 for the height. So let's find our mean first. So if we add up all of these together and divide by 3, we would get the mean, and we're going to get 7.57, and then this one would be 5.0, and the other one we can say is 1.67. So, and the range between each one, so the range for the height would be 7.6 minus 7.5, which is the maximum minus the minimum. So we would get 0.1. Here we have a range of 2 between 5.1 and 4.9. So we have a range of 0.2, sorry. And here we have a range of 0.1. So 1.7 minus 1.6 is 0.1. And to find our absolute uncertainty, we can just follow this equation of the range divided by 2 is equal to our absolute uncertainty. So applying this to each one of our readings, we would get 0.1 divided by 2 for the length, so we'll get 0.05. 0.2 divided by 2 is 0.1. And 0.1 divided by 2 would be 0.05 again. And now to find the absolute uncertainty of the volume, we have two methods we could do this. So method 1 would be to find the maximum and minimum values of the length, width, and height over here. So for example, the length would be 7.6 because it's the maximum value. For the width, it would be 5.1, and the height, it would be 1.7, which is the maximum values. And then we'll just use that to calculate the volume, which would be, remember, volume is equal to width times height times length. For our Vmax, we can use this later to find our absolute uncertainty. So we'll use 7.6 times 5.1, the largest value of the width, and 1.7, which is the largest value of the height. And if we multiply these together, we're going to get 65.892, which we can approximate to be 65. We're going to leave it to two significant figures. We'll explain on the significant figure section, we'll explain more why I leave certain things to certain significant figures. For the minimum height, so V min, we can use the minimum values of the length, width, and height. So 7.5, 4.9, and 1.6. And we'll just multiply them together. And this is equal to 58.8, which we can approximate to 59. And to find the absolute uncertainty, we can just do the same thing as we did before to find each individual uncertainty, which was range divided by 2 to find the absolute uncertainty. And so the range would be the maximum minus the minimum value that we got. But one thing we haven't taken into account the absolute uncertainty yet. In the next way of finding the absolute uncertainty of the volume, we're going to use the absolute uncertainties that we found for each length, width, and height values. So now we've got range. The range would be 65 minus 59, all divided by 2, which would be equal to, say, around 3 centimeters cubed. So our uncertainty would be, we can write it as plus minus 3 centimeters cubed. For our uncertainties here, we can also label it as plus minus, plus minus, plus minus, and they're also in centimeters because absolute uncertainty has the same units as the measurement itself. So the second method of finding the uncertainty, we're going to do the same thing. So find our maximum and minimum values of the volume. And we're going to find our maximum and minimum, instead of finding the maximum from here, we're going to just use the mean and then either add or subtract, hence this sign we've used here, the absolute uncertainty we've found for each of the values. So for example, for the maximum value of the length, we would do 7.57, which was our mean, plus 0.05. And then because we're multiplying each one to find the volume, so width times height times length, we're going to multiply it by the maximum, which would be 5 plus 0.1 and 1.67 plus 0.5 to get our maximum value of the volume. So, and this is equal to the maximum value of the volume, which we get as 66.84 ... and we can just approximate this to be 67. And for the V minimum, we would do the same thing. So to find our minimum, we would just do, instead of adding the uncertainties, we're going to take away the uncertainties. And we are going to get 59.69, etc., which we're just going to approximate to be 60. And to find our uncertainty, we're going to do the range divided by 2. So we're going to do 67 minus 60 divided by 2, which is 7 over 2, which is 3.5. And because we have to leave our uncertainties in one significant figure, I'll explain later why in the significant figure section, we would leave it as plus minus 4, which we can approximate to be plus minus 4 centimeters cubed. And that's how to find the absolute uncertainty. And as you can tell, that we started off with very small uncertainties, so 0.05, 0.1, and 0.05. And now they've gone up to 3 and 4, which are a lot larger. So as you start putting values together and using more values in your equations, you would end up with larger values of uncertainty in the end. Now let's move on to presenting uncertainties. So since we did 2 different ways of measuring our uncertainty, and if you get 2 different values, and to choose our uncertainty, so if you choose both ways and you find 2 different values of your uncertainty or multiple values, you always use the largest as your uncertainty and choose your largest uncertainty as your value for the uncertainty. If you have no uncertainty in your measurements, you will need to find the uncertainty in your instruments. So for example, here we did the uncertainty in our measurements because we took 3 measurements and we found the uncertainty in our measurements. But if you don't have multiple measurements to find the uncertainty in your measurement, you will need to find the uncertainty in your instrument. And this can be found by using the smallest division of your instrument divided by 2 is equal to the absolute uncertainty. And the smallest division, for example, in a ruler, would just be, say if you have a ruler in centimeters and it doesn't show any millimeters or anything like this, the smallest division would just be 1 centimeter. For example, so we will have absolute uncertainties, which can be written like this. So for example, 10 plus minus 0.5, and then you write the centimeters or the units that you have after it, after both of the values. Then you would have fractional uncertainties, which is just a fraction of your uncertainty over the mean value. Your fractional uncertainty would just be written like this, so 10 centimeters, and then you write the plus minus 0.05. So you write the units before, and then you write the fraction after. So now let's move on to, so you can write it, if you can write in fractional, you can leave it as a percentage as well. So, and these can be written similar to fractional uncertainties, where you write the units at the front with the mean value, and then you write the percentage after using a percent sign. And these are your different ways of writing your uncertainties. And just as a convention, we can write that each uncertainty, absolute uncertainty, can be written as x plus minus delta x, which is our uncertainty. And to find our fractional uncertainties, let's make an equation, dx, so this is our absolute uncertainty as delta x, and our fractional uncertainty would be just delta x over x is equal to fractional. And to get your percentage uncertainty, you would just multiply this by 100. And now let's move on to reducing percentage uncertainty. So if we look at the equation of percentage uncertainty, remember we will just multiply it by 100 from the fractional uncertainty, and the fractional uncertainty depends on two things. So you could have the uncertainty, which you can't really get changed much from your readings, because the absolute uncertainty will be pretty much the same. So if you have the same instruments or the same techniques, you would end up with similar absolute uncertainties. But what you can change is the value of x, which is the mean. If you were to read the thickness of a piece of paper, you would have a mean reading of a very small value, like say 0.08 millimeters, for example. And because the way you measure it, or just in general your uncertainty, we can say when measuring any piece of paper, you're going to get an uncertainty, absolute uncertainty of 0.0005 millimeters, because you can't get any more precise than that. So now to reduce your percentage uncertainty, remember it depends on the absolute uncertainty and the mean value. So because we can't really change this fact, we can actually increase this and make this, if we make this bigger, because it's 1, so the absolute uncertainty divided by the mean, if we make the mean bigger, we're going to get a smaller fractional uncertainty. So we can reduce our fractional uncertainty from our reading. This is very useful because later when combining uncertainties, most of the times using fractional uncertainty and percentage uncertainty is used to combine uncertainties together. So how would we make this mean bigger? So one way of doing it, instead of measuring just one piece of paper, you can measure similar pieces of paper, so 10 pieces of paper. If you assume that these are identical, or you're measuring the average thickness of a piece of paper in general, if you measure instead of just one of the pieces of paper, you measure all of the pieces of paper, you could get a mean measurement which looks more like 0.8, which is a lot bigger than 0.08 millimeters. And remember, because we're stuck with the same measuring devices and measuring techniques, we're probably going to have this same absolute uncertainty, plus minus 0.005 millimeters. And now if we were to calculate the absolute uncertainty, we would have, so let's calculate it for the first scenario. So when we're measuring one paper, our percentage uncertainty would be 0.005 over 0.08 times 100, and we get around 6.25% percentage uncertainty. However, if we measure 10 pieces of paper, we would have 0.005 as our absolute uncertainty divided by 0.8 now times 100, and we would get, instead of 6.25%, we're going to get a much smaller value of 0.625%. And this makes a lot of difference when combining uncertainties later on in equations and converting between units. So now let's move on to combining uncertainties, which is a carry-on from what we just did. When you have values in equations, for example, when you add and subtract, you would add the absolute uncertainties together when you add and subtract values. And when you multiply, or divide, you would add the percentage uncertainties together, or the fractional uncertainties. But make sure if you add a 1% uncertainty of one value, don't add it to the fractional uncertainty of the other. Make sure that you're always adding either percentage or fractional separately. Once you choose one, make sure that once you choose one of these, stick to it so you don't mix percentages and fractions. And when you raise to the power, for example, x to the power of a value n, you would just do n multiplied by the percentage or the fractional uncertainty. If you multiply it by the percentage uncertainty, you will get a new percentage uncertainty of the total value, and if you multiply it by the fractional uncertainty, you'll get a fractional uncertainty of the total value. Don't mix them up. It's worth noting that when you convert units, your percentage uncertainty or your fractional uncertainty stays the same. This is when you're converting, for example, from centimeters to meters, meters per second to kilometers per hour, etc. When you're converting, for example, from area into volume, you wouldn't use this rule because you would use this rule instead. So these ones you can convert the units and the fractional uncertainty will stay the same, but for this one it will not. Now let's move on to types of errors. So there are two types of errors. There's either random errors or systematic errors. Random errors are the spreading of a value in an unpredictable way which affects precision. And the most common trait of these is that it's spreading of a value in an unpredictable way. And this is what makes random errors so recognizable. An example we could say is parallax error, which is causing different readings. So systematic errors shift your values by the same amount all the time, affecting your accuracy. This can be caused by environment, your apparatus, or your method. And this can be done through multiplication, adding, or subtracting. So your values could be a multiple more than they should be, an addition more than they should be, like adding a certain amount of value more than they should be, and or be less than a certain value than they should be. And this affects the accuracy. And an example is a zero error. For example, where you measure on a ruler and you start reading from here instead of at 0, your values would be shifted to the right. So they'll be increased, so they'll have this difference because you're not reading from the 0. So this is a zero error. So the main characteristic of the systematic error is that they shift your values by the same amount. And if you spot any of these errors, you will try to correct them. And if you suspect a systematic error, you could repeat the experiment with a different technique and compare your results. So now let's move on to planning experiments. So when we plan an experiment to solve a problem, we'll have 7 steps that we would like to carry out. So the first step would be to make a prediction or your hypothesis, and this is based on experience. The second step is to identify independent, dependent, and control variables. The third step is to create a risk assessment. Your fourth step is to select your equipment. Your fifth step is to decide what data to collect and how to do it. Your sixth step is to make a clear and detailed method so that you can make it repeatable. Your seventh step is to carry out a test to provide evidence for and against your statement. So this is where you finally carry out your test. And these are all steps of planning an experiment to solve a problem. Now let's look at how to make it a fair test. So to make it a fair test, a fair test is done when you control all the variables except the independent and your dependent variables. And this will increase your validity. Now let's move on to experiment evaluation terms. So this is just going to be for definitions of words that we could use, or they could ask you about experiments. So for example, we talked about control variables. Control variable is when you keep them the same, keep the variable the same. The independent variable is the thing that you change. The dependent variable is the one that you measure in the experiment. Now let's look through more words. So for example, if they ask you about accuracy, which we mentioned before, and precision, these might seem the same, but they're actually slightly different, and you can talk about their meanings. So, for example, accuracy means how close your measurement is to the true value. So if we were to draw like a dartboard, let's draw an accurate representation. So say this is the true value in the middle, and if we're taking measurements of the true value, let's see what an accurate measurement would look like. But an accurate but not precise. Let's do that. So an accurate one, we can take points here. We're taking readings all around here. And if we find that our average reading lies here, this is an accurate result because we have an average reading. So we've taken readings and we've concluded that the average reading is actually, so the mean is on the true value. So this is very accurate, but it's not precise. And we'll go to that in a minute. So it's not precise because the dots are really far away from each other, or like the readings are very far away from each other. So the uncertainty would be very large in this measurement. So as we said before, that systematic errors affects your accuracy and your random errors affects your precision. Even if you have random errors, your measurements might look more like this, but if you have systematic errors, they will affect your accuracy. So if we have really high precision, but we have a systematic error, we could have readings that look something like this. All very close to each other, where the mean is right in the middle between them, but they're not close to the true value. So they're precise, yes, because they're close to each other, but they're not accurate because they don't lie on the true value. Now let's add more words that we might need to use. So for example, repeatable, when you can repeat the experiment and get the same result. Reproducible is when someone else can recreate your experiment using different equipment or methods and still get the same results. So the key difference is that one, you can repeat it and you'll get the same result, and the other one, you can recreate it and you can get the same result. A valid experiment is, as we said before, controlling all variables except the dependent and independent variables. And an anomalous result is a result that doesn't follow the common trend, so are not used in the final calculation. All right, let's move on to unit prefixes for different types of units. So to scale up things, you can use different units, and these units have different prefixes and they have the same prefix. For example, like kilo, mega, and we're just gonna go through all of them from the largest ones to the smallest ones. So I'm gonna make a table of the prefix, the symbol. For example, kilometers, you would write K and then M, and the multiplication factor that so for example, kilometers would be 1,000 meters. So let's start with the multiplication factors. We have prefixes for all these multiplications, so 10 to the 12, 10 to the 9, 10 to the 6, 10 to the 3, 10 to the 0, and by the way, these ones are 10 to the 3 is just 1,000, 10 to the 6 is a million, 10 to the 9 is a billion, and 10 to the 12 is 100 billion. So 10 to the minus 1, which is just 1 over 10, 10 to the minus 2, which is just 1 over 100, 10 to the minus 3, 10 to the minus 6, 10 to the minus 9, 10 to the minus 12, 10 to the minus 15, and 10 to the minus 18. And these are all the prefixes. So the prefix would be, for the 10 to the 12 would be tera. For example, terabytes, terameters, stuff like that. Then for 10 to the 9 would be giga, like gigabytes, or like gigameters, gigapascals, giganewtons, for example. The 10 to the 6 would be mega. 10 to the 3, the famous one, which is 1,000, which would be kilo. And then 10 to the 0 would just be itself. So for example, meters would be centimeters, because 10 to the 0 is just 1. So for example, meters, pascals, newtons, etc., joules. And 10 to the minus 1, so a tenth of anything is called a deci. For example, decimeter, decinewton, decijoule, decipascal, stuff like that. Then after that, a hundredth would be centi. That's where you get centimeter. Milli would be millimeter, so it would be 10 to the minus 3. Then it goes on to micro. which is 10 to the minus 6. Then it's nano, 10 to the minus 9, nanometers, for example. And 10 to the minus 12, it starts becoming pico. Then 10 to the minus 15 is femto. And then finally, atto at 10 to the minus 18, which is an incredibly small number. And all the symbols would be T for tera, capital T for tera, capital G for giga, capital M for mega, K for kilo, D for deci, C for centi, M for milli, mu for micro, N for nano, P for pico, F for femto, and A for atto. And these are all the prefixes for all the multiplication factors. So now let's move on to the 7 fundamental units. So most units are made up of other units. And the only units that aren't made of anything else, so like, for example, newtons are just made up of kilograms times meters per second squared, because you got mass times acceleration. And this can be, this is the most broken down you can get. There's certain units that you can't break down any further. So, and these are the 7 fundamental units, and they're called the 7 fundamental units. So these are the ones. So you've got meter, and we're going to leave them in SI units, which is the common standard for units. So instead of kilograms, so for example, instead of kilometers, we're going to leave it in meters, because meters is like the standard that we use for physics. And it has the symbol M, and this relates to distance. Then we have the kilogram, which is kg, and this is SI units again. So this represents mass. Then we have the second, it's written in as S, and guess what it represents? Yes, it represents time. Then we've got the ampere, or better known as the amp. The ampere is a measurement for the currents in a circuit. Then we've got the Kelvin, which is the fundamental unit for temperature. It's written as K. It's not degrees Celsius. So we use the Kelvin, which is our SI unit for temperature. And then we've got the mole, which is written as MOL, and it represents the number of particles, or the amount of a substance. And finally, we have candela, CD, written as CD, and this represents luminous intensity. And for all of these units, you cannot break it down any further. It's not like newtons, it's not like joules, where you can make an equation and find the units of each equation. These ones, you cannot break it down any further. You cannot represent meters as anything more than what it is than its distance, because you can't really describe distance through another thing. You can't explain mass through another thing. You can't explain time with another thing. Current, same thing. Instead of, you might think it's charge, but it's actually current that is the fundamental unit instead of charge. The temperature, you cannot explain it with any other thing. And mole is another fundamental unit, which you can't really explain the number of particles in a thing with anything else than the number of particles themselves. And the same for candela. So these are the fundamental units. There's 7, and you cannot break these down any further. Now let's move on to combinations of units. This is just a quick reminder. So from GCSEs, you can write meters per second like this. So this is GCSEs. But now for A-levels, you can write them like this. Meters per second, where the power just basically represents the per second. And the same for meters per second squared for acceleration. You would write this instead as meters per second to the minus 2, which just means the same thing, but you just put it all as in the power and you multiply them out like that. It's just nicer to leave it, and it makes you understand what each power has and what each fundamental unit or each unit is raised to the power of, so you can compare the units of equations, so it's dimensionally consistent. So anytime you have a slash, you can now replace it to the power, so whatever's beneath the slash, you'll turn it into the power of a negative, whatever power it is up to, like this. So now let's move on to significant figures. And significant figures are very useful to know like how they work, and to know what significant figures to leave your values in is very important, because significant figures, they show uncertainty. And always remember, just assume your largest uncertainty in your data. To assume your largest uncertainty means to leave your data with the least amount of significant figures. I'm writing significant figures as s dot f, by the way. For example, let's do some examples. Say we have 15.5 times 2. We don't have any uncertainties on this data, so we would get 31 if we multiply these two. However, because we are assuming the largest uncertainty, we will leave it to the same significant figures as the least possible in the calculation. So for example, this one has the least one is just 2, which is just one significant figure. So we'll leave the value as 30 instead of 31 because we will just round to one significant figure. Let's do another example. Say we've got 15.5 times 2.0. Now, because our least value would be left as two significant figures, the 2 and the 0. Remember, significant figures include the zeros after. So say 15.5 has three significant figures because of the 1, 5, and the 5. And because it has no zeros after, it has only 3. But this one has 2 because the zeros after do count. So in this case, you will leave this as two significant figures, so you will leave it as 31 as your answer. But if you have something like this, that 15.50 times 2.00, now this is left with four significant figures and this is left with three significant figures. You would assume the largest uncertainty, so you would use the least number of significant figures, which is 3, so you can leave it as 13.0. And this 0 adds just another level of accuracy, so we know that it's not 13.1.1 in our readings. It's not 31.2, for example. We know that's exactly 31.0, but it could be 31.01, 31.02, for example. Like, we don't know what this one is. That's why I leave it to this level of accuracy. Because we had no uncertainties here, if you have no uncertainty in your measurements, you can just estimate your uncertainty using the amount of significant figures. For example, if we have 2 newtons, written like this is our data, and because there's one significant figure, we can write this out as 2 plus minus, and because there's one significant figure, we can just estimate the accuracy to be plus minus 0.5, and we can write this in newtons. Because that's one significant figure after, so we've got one significant figure, and because after 2, we can get 2.0, and because we don't know if it's 2.0, 2.1, 2.2, we'll just do plus minus 0.5 because it can go all the way up to 2.4 or 2.499999, or from 1.5 because those are the upper and lower bounds, for example. So you can round 1.5 to get this, and you can round 1.49999 ... etc. to get this. So that's why we do the plus minus 0.5 newtons. And this is very important, like how we leave our uncertainties, because the number in front, so this number here, the number in front cannot be left to a higher precision than the uncertainty. So say if we have this value here, and we say it's 2.315 plus minus 0.5 newtons, this is impossible because now we're saying that it has this extra level of accuracy, and then we're saying that it doesn't have that accuracy because it's plus minus 0.5. Because these numbers could be arbitrary, because we're saying it's plus minus 0.5, so it can be between 2.815 and 1.815. This extra, because there's so much difference between these two, there's no point of writing these extra two values, so we can just leave it as the 2.3 plus minus 0.5. And this is possible because this is not a higher precision than the uncertainty, so we can leave it like this. So this one is wrong and this one is right. So most uncertainties are left to one or two significant figures, because say we had 2 plus minus 0.51234 newtons from the example from before. We can't really do this because now we're saying that this has an extra level of accuracy, because it can be between either 2.51234 or 1.48766. And these in itself, they are so accurate, they're so precise. Why exactly these values so precise all the way up to those many significant figures, when we can just leave them to 0.5, when we can just make it our life easier by leaving it to 2.5 and 1.5, which is just 2 plus minus the 0.5 from before. So we never leave uncertainties to more than two significant figures. And rarely, most of the uncertainties, you would rarely see two significant figures for uncertainty. So normally most uncertainties are left to one significant figures. So it's very important to remember this. Let's recap quickly. So we have to leave your uncertainties to the smallest number of significant figures as you're assuming your largest uncertainty when you're combining values. So you leave it to the smallest number of significant figures to assume the largest uncertainty when you're combining values. Then remember, you can assume the uncertainty on a value without knowing its uncertainty just by looking at the amount of significant figures it's left at. And then remember, we can't leave uncertainties to a larger accuracy than the uncertainty, because it will just add unnecessary significant figures after, which can be rounded and left at a better accuracy. Can be rounded because these are meaningless, basically. And last of all, we have that you can't leave the uncertainty to many significant figures. Best to leave it to one significant figure, because again, you're going to get this unnecessary level of accuracy, which doesn't mean anything. So you might as well round it. Now let's move on to types of data. So now we're going to look at the 4 types of data and also types of correlations that we can get from the data. So say the first type of data is discrete data. And this is when you get data by counting and you only get positive whole numbers. Then we have continuous data, which is when when the data can take any value on a scale. So like you can add as many decimal places to the value and it will still be continuous. So you can do like between 0 and 1, between 0.5 and 1 and 0.75 and 1, and keep going. And you can get as much detail as you need. So this is continuous data. Then we have categoric data, and this is when you have data that is sorted into categories. For example, wood, glass, steel are different categories of materials. And then we have ordered data. And this is very similar to categoric, but in this case they have order. And an example of this would be low, medium, high. And now let's go into different types of correlations that can be shown in data. So say we have a graph like this. If you have data points that look something like this, if you were to draw a straight line, or like a line representing the data, for example, best line of fit, this would be a positive correlation. And if you have data points that look something like this is called a negative correlation. And when you have data values that look something like this is when there is no correlation. And this could also look something like this. And this could be another type of no correlation, because if you increase one variable, by the way, each of these graphs is one variable against another, and they have a correlation between them. And because if you have one variable changing and one stays the same, it doesn't change at all, that means they have no correlation either. Now let's move on to estimation. So when you estimate, you always estimate to a power to 10. So x to the n, for example, x to the any number, you always estimate. For example, 86400 approximates to be 10 to the 5. 400620, we can approximate to be 10 to the 5 as well, because in this case you round up, because you have 1, 2, 3, 4, 5. You can write this out as 8.64 times 10 to the 4. When you round up, you get 10 to the 5. Or this one you round down, go from 4.0062 times 10 to the 5, which approximates to 10 to the 5. And you also need to estimate using common knowledge. For example, let's do some practice. What is the weight of a piece of paper? You can approximate to be 1 gram, or 10 to the minus 3 kilograms. See, we leave it to a power of 10, like that. This is a mass for paper, for example. Then with the volume of a sink, you could approximate it to be, you can guess it to be, say, 0.5 meters cubed, but we approximate this to be 10 to the minus 1 meter cubed. And this is for the volume of a sink. But in this case, we could approximate it maybe 0.2 instead, because we're going to have to round down to get to this, because I think 0.5 would be a bit too much volume for volume of sink. And for the height of a tree, a random tree, we could say a tree is between 1 and 10 meters. So we can approximate it to be 5 meters. And then this we can approximate it to be 10 to the power of 1 meters. And this is for height of a tree. Now let's move on to the vernier caliper. So if I draw a vernier caliper, it will look something like this. And let's annotate it. So here we have two rulers. So we'll have a first ruler here, and this is a second ruler. And we can understand how it works. The first ruler and the second ruler are offset by a degree of precision. And let me draw this out, how it means. So if we have the first ruler that looks something like this, from 0 to 1 centimeters, the second ruler is offset from 0 to 1, adding a second degree of precision because it is offset by this small amount. So to read the vernier caliper, so we also have tweezers in the vernier caliper, which are these two over here. And if we put an object inside like this, so if you have an object which is pinched between the tweezers like this, that's how you measure so you're trying to find the distance of the object over here. To measure its distance, you would look at where 0 of the small ruler is and see where it lies on the big ruler. And this will give you your first significant figure. And see it lies just after 5. So this will be our significant figure. We will say is our first one would be 5 centimeters. So this is all in centimeters. And now what we would do is measure on the second ruler a point where one of the values of the second ruler lines up perfectly with a value on the first ruler. So if we look, this one's offset, this one's offset, this one's offset, this one's offset, this one's also offset, but this one is actually in the right spot. So it's actually lined up properly. So the value would be 5. So our second significant figure would be 5. So our reading would be 5.5. So in this vernier caliper, we could leave in centimeters because we're not showing the millimeter accuracy. But basically, if we had a vernier caliper where this was in millimeters, and we would have a more like a 0 and then the small lines like this, we could find the value to millimeters precision plus an extra decimal place using the second ruler. But in this case, because we have this, we can't draw the millimeters on the ruler, we're going to leave in centimeters. So, but if you were to have a millimeter ruler, you would measure where the 0 is at on the millimeters. So it would be like, say, 5.6 or 7. That looks like 5.7. And then you add on the extra decimal place using the line up here, which would be 5. So you have 0.05 of extra accuracy. So you would get 5.75. And that would give you an extra accuracy. So that's why the vernier caliper is so useful, because it gives you that extra level of accuracy that a ruler doesn't give you. And it's also very useful because you can modify your tweezers to measure inside things. You can also modify them to, or just how they are here. You can measure the distance of things or the length of things. They have an attachment at the end where you can measure the depth of things as well. So something like this. So you could either measure inside things, the size of things, or the depth of things. And now we've covered the vernier caliper, let's move on to the micrometer. So if I were to draw a micrometer, it would look something like this. And you have a scale here, and you have a rotating scale over here. So this one's rotating. This knob over here is very useful because it applies a constant force when tightening the micrometer. And this is very useful because then it doesn't squish the object and it doesn't get elastic properties involved in the measurement. So it applies a constant force. So you would measure your object over here, and then you would measure the value on this scale. It gives you 0.5 extra of a precision up to 0.5 millimeters. So this would be in millimeters, and it gives you up to 0.5. So if we were to measure this, we would get 4.5 millimeters, and then we're going to add on the precision from the rotating part here. And this would be like a scale that goes all the way around from 0 all the way to 50, which is 0 as well. and it gives that extra precision of the 0.5. So here we measure, it would have to line up with this part here of the shaft. And in this case, you would have 45 as your value. So you would add on 0.45 millimeters to your precision. And then the reading of the length of this value would be 4.95 millimeters of the length, which is a very high precision. It's worth noting that micrometers are prone to zero errors. And that's the end of this whole topic for uncertainties and their errors. Thanks for watching. I hope this was useful for you.